Okay, good afternoon. I hope I'm audible. There has been an issue with our server. I cannot access my presentations. Actually, it's an overleaf document, and it's not available offline at the moment. All the files are online, and unfortunately, we have ran onto a server issue. I'm not sure whether it is from our end or it is from overleaf's end. So, unfortunately, at this time, I won't be able to discuss the summary of the topics that we covered in week 5 because all the slides are at the moment is not available with me because of the server issue. However, I may be able to solve some sample problems if sample problems for week 5 because I have all the files, I have all the images with me. But yeah, if you in case if you have any doubts regarding week 5, you can always let me know. I can stop and make sure that the doubt is cleared to the best of my abilities. So yeah, we'll start with yes, we'll start with the session. We'll just directly go on to the problem solving session uh, I am unable to share my presentations at the moment. Okay, so let me open the files. Okay. Okay, so we'll get on with the topic. We were mostly, let me see if I can bring this to full screen. Okay, so we were mostly dealing with the topics on localization. So earlier we have covered mostly on perception, the topics on perception that was on week 4. So on week 4, we covered perception. And on week 5, that is what we are discussing for this week, we covered the topics on localization. Right. So this is what we would be covering for this week, all the topics regarding localization, how to uh, model or how to develop this error modeling, odometric error modeling for a differential wheel drive, and how it propagates. Like if there is an error on the sensors, the reading sensors, how would the error propagate from the sensors to the estimate of position, and what are the uncertainties that would accumulate, and later using sensors, so using sensor fusion, how can we reduce the uncertainty so that we can get a better estimate of position. So all these topics are basically comes under localization, which is what we have, which is what that has been covered for the lectures of week 5. And yeah, so we'll try to solve a few problems for regarding all the topics in week 5. So yeah, the question says, given a differential drive robot which localizes itself in this environment using the odometry based wheel based on the wheel sensor readings. So select the deterministic errors that can be eliminated by proper calibration of systems. So in the last week and this week, we have come across the term deterministic error and non-deterministic error. Another term for this non-deterministic error is what we call as random error. So uh, the basic classification of errors, what we have is what we call as deterministic errors. And on the other side, we have non-deterministic errors. And we also call this by another name called random errors. And in the case of deterministic errors, we can basically eliminate them through proper calibration of systems. Whereas non-deterministic errors, it cannot be fully eliminated. But however, we can model using probabilistic methods, we can actually model the distribution of random errors using some probability distribution function. That's all we can do, but we cannot fully eliminate that. So the question was to select out of all these possible cases, we have to select what are the possible sources of deterministic errors. Yeah, the first would be the limited resolution during integration. So does that come under deterministic or non-deterministic error? So yeah, the limited resolution of in during integration cannot be fully eliminated because it also depends on the measurements, measurement accuracy, and yeah, there will always be some sort of error. Because of the presence of noise and sensor inaccuracies, there is always going to be some sort of random errors. So the resolution as well as the resolution, whatever we are actually gaining from the sensors, for example, an encoder, we would be getting the velocity from the encoder. So if you want to find the acceleration, we will have to integrate it. So due to the fact that the sensor reading itself is inaccurate and probably could be riddled with noises, integrating could possibly accumulate whatever errors that we have already measured. So on further integration, the errors could keep on further getting accumulated, which cannot be fully eliminated. However accurately we calibrate, or however how, or even if we select, even if we go for a higher resolution, on integration it may further accumulate errors. So option A may not be the right choice because that could come under random errors. So what about option 2? Option 2 is basically denoting uncertainty in wheel diameters, and in particular unequal wheel diameters. So yeah, what happens if the wheel diameters are not equal? So the easiest way to diagnose this issue would be like if all the wheels are given the same angular speed or the same input velocity commands, we expect the robot to go along a straight line. For example, if we drive the motors in one direction, the robot should move in that specific direction with zero angular component. It should go straight. But if the robot is actually not going in a straight trajectory, if it is deviating, if it is turning sideways, then that means that the robot could have some issues with the wheel diameter. Most probably, the wheel diameters may not could be unequal. So if you feel that even if you give the equal inputs to the wheels, if the robot is actually moving sideways, or if it is not moving in a straight line, so then that means yeah, then it means that the system is uh, yeah, the system is actually of unequal diameters. It may not have equal diameters. So like why we and most of the cases we can more or less with a very small tolerance we can easily find or easily manufacture wheel diameters more or less of equal size. So that is a problem that is not a problem that we need to worry too much about because of the manufacturing processes, uh, recent advances, we can easily make sure that the wheels are more or less in the same diameter. So option B is a good candidate of deterministic error. So that makes it so that we can eliminate it using proper calibration. And option C basically says variation of contact points of wheel. So that may not be a thing that you can influence on because the contact point not only depends on the wheel of the robot. So even if you have uh, accurate or perfectly circular wheels, the ground may not be as smooth as possible or as flat as possible as you would expect. So that is also out of your control. You cannot make sure it's since the contact point is also influenced by the environment. You cannot fully eliminate, or you cannot have a full you cannot fully influence the contact point of it. So again, that also becomes a source of random error. This is also a source of random errors, right? Then misalignment of wheels, again, like similar to how we have diagnosed unequal wheel diameters. if you feel that the wheels are actually with equal input velocity commands, if you feel that the robot is actually moving away from a straight line, then that could also be a possible cause of misalignment of wheels. So since it is a part of the robotic system that you are investigating, or you are developing, that is fully under your control, you can basically have full control or full influence of these sort of things. So this can also be fully eliminated using proper calibration. This can also be fully eliminated. So this is basically deterministic. And if you take a look at option number 5, what do we have? In case of option 5, it says unequal floor diameters. So again, that is also out of your control. You cannot you cannot have a full on influence on the floor contact, because the floor is basically part of uh, the floor is actually part of this environment. You can influence the wheel which is in contact with the floor, but that is the extent to which you can have a control on this issue. But the floor and the environment, you cannot have a full on influence. So this also is a source of random errors, right? Okay, so since we have covered all the 5 options, then which is the correct, which could be the correct option for which all could be the correct option for this question? I label this as question 1. So it says deterministic error. So we have established that option B is the source of deterministic error, and option D is also a source of deterministic error. So the correct options are option B and option D in that regard. Okay, so we can move on, I suppose, with this. Okay. So yeah, I won't be discussing this answer key. We have this answer key with me. So options A and D are indeed the correct answer. So the biggest issue is that I cannot access my PowerPoints yet. So that is this issue. Uh, yeah, and because of that, we are restricting ourselves to the questions and answers. Okay, so this has been, I couldn't, anticipate this. This issue has been unprecedented. So yeah. Okay, so yeah, moving on. I'll upload the PPTs. You can access the final version of the PPTs that will be shared to you just like usual. So that will also have the consolidated summary of all the topics that we discuss that we should have discussed during this session. Okay, so question 2 is a numerical problem. This is question 2. So it says a differential drive robot at initial pose A is given as P as 2, 3, 25. So the initial position coordinates are given as 2, 3, and 25. And I hope you can identify which all coordinates these are. These are Px, Py, and theta. Because for a differential drive robot, the 3 degrees of freedom are, the motion along x-axis, the motion along y-axis, and the angular component theta. And the theta is actually given in degrees. It's not, even though it's not specified, it's actually in degrees. In your questions, it will be specified degrees, but in this case, it's simply given as a numerical value. And the question says, given this initial position, the robot moves to another point B, right? So from an initial point A, the robot should move to this final point B. So given the distance between the two wheels as 1 unit, so I'll roughly draw the configuration of the differential drive robot. So these are the wheels, and these are the body fixed frame of reference, X and Y. And the position coordinates of this frame is given as 2, 3, and 25 degrees. Yeah, and the distance between the two wheels is given as 1 units, right? Okay, so for further, it is also said that the right and the left wheels traverse a distance of 3 and 2.5 units respectively. So if you consider this as the robot along the longitudinal direction, this is considered as the right side. So this is delta SR. This is considered as the left side, that's delta SL, right? So the direction along positive y-axis is considered to be the left side, and the direction along the negative y-axis is considered to be the right. So what is the absolute traverse distance of the robot is? So this is a simple kinematic problem. So if delta SR and delta SL is given, the the distance the center of the robot moves is nothing but the average of the distance moved by the right and the left wheels. So it's nothing but delta SR plus delta SL by 2. This is delta S, right? If the right wheel moves by this much unit and the left side wheel moves by this much units, the total distance traversed by the robot is simply the average of the left and right wheels. And the total distance traversed by the robot is nothing but the distance traversed by the centroid of the robot chassis. So if you do this, if you substitute the values, delta SR is 3.3 and delta SL is 2.5, and the average of this is 5.5 by 2. This will be 2.75 units, right? So yeah, in that case, the answer is directly given. It is 2.75 units. Okay, so yeah, I don't think there should be any confusion regarding that because all these formulas are, it has been already discussed during, yes, during the course, during the week 5 lectures. So I hope there is no scope for any confusion regarding this because these have already been discussed during week 5 lectures, right? Okay, so yeah, moving on to question number 3. Let me see. Okay. Okay, so question 3, again the same problem. So I'll write it here. Delta SR is, I suppose it was 3 and delta SL was 2.5. This is a continuation of the previous question. What will be the change of pose from position A to position B? Right, so you know that the new position P dash would be given as the current position Px, Py, Pz plus delta Px, delta Py. Sorry, this is not Pz, it's delta theta. For the mobile robot, the three coordinates are Px, Py, and theta, and delta theta. So how do you find this delta theta? And again, delta theta is also nothing but delta SR minus delta SL by 2 times the distance between, the distance between the two wheels. So we have already covered this, how to get this thing using the kinematics of mobile robot. If you can recall, you know what is the relationship between UVR and omega. We have a W matrix, right? A configuration matrix. So if you want to know the theta, the final coordinate, you know how it should be. It's nothing but the angular position of, it's nothing but the difference between the relative motions of right and left wheels divided by the distance between the two wheels. So in the question, it is all these values are given. If you simply substitute it, this is 3 minus 2.5 by the distance between the two wheels was given as 1 unit. So this is nothing but 0.5. Delta theta is 0.5, right? So delta px would be delta s cos theta plus delta theta by 2. Because this is the change in x, change in y is given as delta py is delta s sine theta plus delta theta by 2. This is basically an interpolation, an interpolation of first order inside this bracket. Theta plus maybe a small change of theta, delta theta by 2. And again, all the values are available. Delta S we have already calculated. Delta S was found to be, I think, 2.75 from the previous question. So we have all the necessary numerical values. We have delta S, we also have delta theta to be 0.5. Theta was already given in the question as 25, right? I think there is nothing else we should be we should be needing. So if you substitute all the values onto that, we will get delta x to be around, I think, 2.4873 and delta y to be 1.1731. And delta theta we have already found out. Delta theta was already found out to be 0.5. So in that regard, the correct answer would be option B, right? The relative change of position is given by these equations, delta px and delta py. Delta theta, we have already found it out. Okay, so yeah, that's about it. 2.47 for delta x and 1.17 for delta y. Okay, so yeah, we'll move on to question 4. How shall it see? Okay, for question 4, it says find the y coordinate of the robot up to 2 decimal places. So as per the question, the original y coordinate was, original position coordinates were 2, 3, and 25. And we have also found delta p, that was, from the previous question, we have found delta p to be 2.4873, 1.1731, and delta theta was 0.5. And what will be the new coordinate of y? So y coordinate would be nothing but the sum of the second element of p and delta p. So this will be 3 plus 1.1731. So this is approximately 4.1731. If you truncate it to 2 decimal places, as asked in the question, the correct answer would be around 4.17. This should be the correct answer. Okay, so yes, moving on to question 5. What will be that? Okay, so question 5 is choose the true statement. It's about prediction and perception regarding that. So yeah, we'll go with the questions one by one. Prediction update is based on the updated belief state. Perception update decreases the uncertainty of the robot as the robot moves. Action update is based on prior belief state. Prediction update increases the uncertainty as the robot moves. So in localization, what were the two different kinds of updates? So we have two updates, what we call as prediction update. Another name for this was action update. Right, and another, the second stage would be perception update. This is also known as measurement updates. Okay, so how is it relevant to a mobile robot? In motion. So, for example, if this is the current state xt, uh, so it also has its covariance available at time t, maybe for time t, and based on a control input ut, it will using odometric using odometry using purely data from its own sensors, it will actually get a new estimate of its position xt plus 1 from its own uh, odometry, actually from its own position and the control input. So earlier, if this was the uncertainty basically grows after the prediction phase. So prediction phase is is simply so prediction is nothing but the probability that the robot state is estimated given the measurements. Sensor measurements are available from the current time to the previous time and the control input. Control input. What is it? Yeah, control input u of e. This is prediction. So just before taking the measurements, measurements from the sensors, the current state is more or less estimated using prediction, and in perception, it's nothing but the probability that the robot is at current position given the sensor readings from the current position, from previous position to the current position, and all the control inputs. So this is, right after ut, but before zt, before the measurement of sensor. This is right after the sensor measurements. Right. So because of this fact, because of prediction, the uncertainty. So for example, if you are beginning from this initial position, so the initial, you know how this error propagation law is. Error propagation law, the covariance of the current estimate would be fp, then qp, fp transpose, then fq, qu, fq transpose. So this is the Jacobian, or this is basically the covariance due to the odometry, contributed from the odometry, and this is basically contributed by the sensors, the wheel sensors, maybe the encoders. So initially, if you consider the robot is moving from a known position, the covariance metrics could be, you could consider it to be zero. There wouldn't we are fully certain of its current position. But as the robot actually moves, this uncertainty increases because of the uncertainty in this QP and also this uncertainty in the sensor readings. So right after the prediction update, the uncertainty from the previous state increases when it is newly estimating, right? And it can be brought down after this perception update. So prediction only relies on the encoders and the control input. And based on the perception, like if prediction basically tells basically lets the robot know its current location based on its map. If a map is actually pre-inbuilt on the robot, but if the robot senses that it has moved maybe 5 units, it can basically correlate what it sees. It can basically find its position from its map, since once it has moved 5 units. But if it is seeing the same thing as it is seeing from the map, using from the sensors, then it can be pretty much certain that its current position is accurately estimated, right? The measurements from the map and the measurements from the sensors are matching, then the uncertainty goes down. Otherwise, if you are purely relying on prediction, the uncertainty keeps on increasing higher and higher. So yeah, so in that regard, prediction update is based on the updated belief state. No, it's not correct. It's not based on this updated belief state. It's only it's actually based on the current belief state. It's not based on the uh, updated belief state. So prediction is solely based on current the odometry and the correct answer. So in that regard, this option is false. What about option B? Perception update decreases the uncertainty as the robot moves. So, if you are purely relying on a prediction, the uncertainty keeps on increasing, but it can be brought down if you are if you are fusing the estimation of from the prediction with the estimation from the sensors, which is what we call perception. So, yeah, in that regard, perception update basically decreases the uncertainty as the robot moves. That is a correct statement. And what about option C? Action update is based on prior belief state. So action update is also called, yes, action update is also called prediction update. Both are essentially the same thing, prediction or action, as I have highlighted over here. Okay, this one. So action update is based on prior belief state. So that is in fact true because it knows what it is. It should know what are the control inputs prior and what is the state of the robot uh, before before its current position. So that is indeed true. And prediction update increases the uncertainty as the robot moves. That is also true. If you are purely relying on odometry, the uncertainty keeps on increasing. It the bounds the errors keeps on growing without any bounds. So yeah, just to clear it, action update is based on prior belief state, but the perception update is based on updated belief state, right? So whatever belief state the prediction is actually having, the perception essentially updates it or basically gives a better estimate. Perception gives a better estimate of the predicted state using the readings from the sensors. Right? So whatever the prediction sees in map, the perception update matches what the robot sees in map and what the robot sees through the sensors. So in that regard, the correct options are options B, C, and D. All right. So yeah, moving on to question 6. With Okay, so it says Markov assumption made in Markov localization is given as. So yeah, what we have basically covered two different uh, principles of localization. So one was this Markov localization in the week during the weekly lectures, and the other one was based on Kalman filter localization. And all the points discussed here are mostly relevant to Markov localization. So we will go with one by one. So only the current sensor measurements are required for accurate required for accurate localization. Just the current sensor reading. So that is obviously not true. It is not solely relied on sensor readings. It is also relied on odometry it's also relied on sensors. So in that regard, only the current sensor measurements are required for accurate localization. That is not a complete sentence, and that is not even true. So that option is actually false. Option B says the current state is only dependent on the previous state and its most recent action and perception. So current state only dependent on the previous state and its more recent actions and perception. Is that true? Because if you have a robot, if it is moving from a previous state to the current state, if this is xt, due to the influence of a control input. So if you call this to be the current state, it is for sure influenced by the previous state, because previous state and the control input is basically will give you the estimation of the current state, right? And this is what we call as the most recent action. So current state and most recent action is nothing but the control input. Am I audible? I hope I am audible.
Yes, sir. You're audible.
Okay, so yeah, I was discussing. I have a technical issue actually. I couldn't access my slides yet. The only thing I have at the moment available is the questions. So I hope my screen is still being shared.
Yes, sir.
Okay, so the problem is that I couldn't access my slides. So
No
the
problem.
format that we have been following until last week, I couldn't keep it up.
No problem, sir.
Yeah, so I couldn't give you the summary of the topic we have discussed. So it's like I have to restrict myself to the questions and answers.
No problem, sir.
Yeah, okay. So yeah, maybe if since you have joined just now, I'll basically start this question once again. So I hope you have gone through the weekly lectures because summary
No,
wise.
sir. I did not go through. I was basically looking at this course for a more mathematical analysis, sir. When
Okay,
I
okay.
looked at this one, everything looks for me as a theory.
Yeah,
Theory, I feel like I will forget after 2 days. But if I get a mathematical understanding of what's happening, that will further
regarding
enrich
week 4. Is it regarding week 4 or regarding week 5?
whatever you are sharing now.
Yeah. Okay. Because even though I was not sharing anything mathematical, I thought of giving some insights using my slides.
Okay.
Because these are the even yeah these I agree with you, because these theories are actually very easy to forget.
Correct.
But
Whatever mathematical intuitions you develop, whether it's
yeah,
robotics or machine learning or whatever it
yeah.
is, these will
Hmm.
help us to further understand those courses better. That's the
Okay.
reason why I have come for this course. And first 2 weeks, that served my purpose. I
Okay.
don't know how the later weeks will be with respect to that.
Yeah, maybe if you are only here for the mathematical topics, then you have to come back from week 7, because
Okay.
week 7 we deal with the trajectory planning, and
Okay.
yeah, week 7 and week 8 is also more or less theory. It's just like an appendix kind of a thing, different kinds of mobile robotic systems. But week
Okay.
7 we basically discuss, I think, trajectory planning.
Okay.
But this is
No
also
problem.
actually very important. If you want to make a robot autonomous, how to fuse the data from sensors and how to rely on the odometry. Those are also actually important. But just in the similar to how we have demonstrated the kinematics and dynamics, we are not fully solving or demonstrating it as its working principle. We are simply covering it principles. That's all we are doing for weeks 4, 5, and 6. But Yeah, again, I think the topics are still very important. It's pretty much integral to the pretty much integral to any mobile robotic systems. But unfortunately, I couldn't discuss all the principles, or I couldn't
No
give you any
problem.
sort of intuitions actually
No,
because of this
no
current
problem.
limitation. Yeah.
Whatever you are doing is you're doing your
Okay.
best.
So
It's really helping us.
yeah, okay. So I'll try to, if the server comes online, I'll try to upload the slides, or if possible, I can, I'll record this tutorial session online, like how I intended it to be, and maybe I'll upload it so that you can access it later.
Sure, sir. Okay.
And if that because of that, I am not even sure whether this current session, what I'm currently doing now, is probably not going to help you because it is more or less just discussing the questions. So
Okay.
I feel without covering the summary, or without covering the topics in brief, this may not be easily followable. But what the questions that is being discussed, because
Okay.
these are more or less theoretical questions, actually, more or less theoretical. So yeah. So, like, I'm not compelling you to sit through this entire section. If you feel like maybe you can, follow it
No
up
problem.
later,
Yeah.
you
No
can
problem.
actually, yeah, okay. So I'll resume this session. So the question was regarding Markov assumption made in Markov localization. So as I was talking earlier, there were actually two different principles of localization. One is called Markov localization, and another being using Kalman filters. And the question basically says, what are the assumptions that we make for implementing this Markov-based localization? So yeah, essentially, it says only the current sensor measurements are required for accurate localization. So we have established that that is false, because apart from the current sensors, we also need the data from its encoders. So it should also need its data from its exeroceptive sensors. So yeah, it could be a bit confusing because there are two sorts of sensors that we are talking about. One is actually the proprioceptive sensors within the robot, like encoders used to track the position of the wheels. And the other sensors are basically exteroceptive, used to perceive its environment around it, the obstacles, or, maybe some landmarks, are landmarks present within the environment. So if the robot was in a state, a prior state, maybe xt minus one, and if the robot is actually, if the robot is currently at a new state, so basically, if you are giving a control input ut, so again, I'll label this as prior state, and this would be the current state. Xt would be the current state, and it basically realizes the current state from the prior state because it has been supplied with the control input ut. And what this current state is simply is nothing but the mean. It's only a mean position of the regions that it could be possibly with, because all these states are associated with some sort of uncertainty, characterized by the mean xt minus 1 and standard deviation sigma t minus 1. And the current estimate is also characterized by its mean xt and its deviation, or its variance sigma t. And if you're purely relying on this odometric sensors, this uncertainty keeps on growing. As you go forward, it keeps on growing. Unfortunately, I couldn't give you this intuition behind how it is growing. But if you implement what has been taught in the lectures, you can. It's if you simply implement that, the error propagation, you can actually see that as time passes, the uncertainty keeps on growing. So the first option says only the current sensor measurements are required for accurate localization. So that is not false. You, apart from the current sensors, you also need an estimate of the previous state as well. The previous state, not the current sensors alone. So that option is indeed false. This is actually false. And regarding option B, the current state is only dependent on the previous state and its most recent actions and perception. So that pretty much makes a somewhat more sense, because if you call this as the current state, xt as the current state, the previous state is xt. The estimate, the odometric estimate is mostly influenced by the control input ut, and that alone will not be sufficient, because as you can see, the uncertainty is even higher than the previous state. But if you fuse this, the estimate with perception, what you perceive from the exteroceptive sensors, you can essentially bring down this. You can essentially bring down this uncertainty if you fuse it with this perception phase, because the robot will be having its own map, and based on the control input, if the robot is in one state, and if you are giving an input to the robot, so commanding it to move 3 units, so based on its map, it can easily locate its position on the map. So the robot should be in a particular location from its map, and from the exteroceptive sensors, it should be seeing whatever it is expecting from the map. So if if the features from the map and the features from the exteroceptive sensor are matching, then the robot can conclude that it's more or less, its current position is estimated more or less accurately. So the uncertainty comes down. But if the features in the map and the features from the sensors are not matching, it has to do some sort of further correcting steps so that its position can be even accurately estimated. So option B is indeed true. The current state is only dependent on the previous state. That is correct. And its most recent action, that corresponds to the control input, and perception that comes from the exteroceptive sensors. Okay, so what about option C? The probability that the robot state equals the actual robot state is maximized. You cannot fully guarantee that. So robot estimates, the robot current estimate and the actual robot state, it cannot be fully maximized. Uh, it can only be given as a probability. For example, if you have seen the Markov localization lectures, there is actually a case study, and at the end of the perception, you can actually get a probability for all the states. For example, Markov distribution basically deals with, the first step is basically discretizing the entire space using grids, and through the prediction and perception updates, and analyzing the map and the measurements from the sensors, the probability that the robot is in all of these grids are basically estimated, right? Through prediction and perception updates, and which are grids gives you the maximum probability. That is where the robot is most likely to be. Right, so it cannot be, it's not essentially fully maximized. It only gives you a probability where the robot could be, where the robot most likely to be in a current on a current instant. That is all it is doing. Okay, so that is also not correct. So option 4, the tracks the robot and is inherently very precise and efficient. So yeah, that is again not the feature of Markov localization, because the basic principle deals with discretizing the entire space, or the entire space where the robot is operating, into multiple into grids actually. So the state estimate basically corresponds to evaluating the state, evaluating the probability, the robot that is in the current position for all possible elements of this grid. So every time the robot is updating, the probability will have to be updated for each and every element of the grid. So that makes it inherently inefficient. It's not efficient, it's inefficient. Because every time this entire grid will have to be updated. So yeah, in that regard, option D is also not correct because fundamentally Markov localization deals with discretizing this entire grid, entire workspace into grids. So the only option that makes sense with Markov localization is option B, and the rest does not even apply to Kalman filter. Also, it's more or less false. Okay, so yeah, this was question 6, I believe. Moving on to question 7. Question 7 basically says state the false statement. So in Markov localization, to update the probability of all positions within the whole state space at any time requires a discrete representation of the space. The required memory calculation and power can thus become very important if a fine grid is used. So we have just discussed that Markov localization basically comprises of discretizing the space into finer grid. So that inherently makes it more inefficient and power hungry. So that is a false statement. So sorry, that is a true statement. The statement is true, but we are looking for false statements. So this is a true statement. And what about option B? Option B states Markov localization starts from any unknown position. So that is also correct because even if the initial position is unknown, the Markov localization eventually can find the position of the robot. So unlike Kalman filter will have to know its initial position so that it can localize it later on. But if you kidnap a robot from the current position and if you deploy it on some other location, Markov localization is actually capable of localizing the robot, even if you kidnap the robot from its current position to a different position. So that is also true. Then what about option C? In Markov localization, the recovery from ambiguous state is not possible. So that statement is actually false, right? Because these are more or less contradicting with each other. We have already established that option B is true. Option C basically says Markov localization. If you kidnap a robot from the current position and if you deploy it on another position, Markov localization is still capable of recovering its sense of position. It is still capable, Markov localization. Whereas Kalman filter, it is not capable. It should know its current position, or if it is starting from an initial position, it should exactly know its initial position. If you kidnap it and deploy it in some other position, Kalman filter will fail, but Markov localization can still, come back and it can easily recover its position after maybe a few iterations. So C is false. And what about D? D basically says Markov localization tracks the robot and is inherently very precise and efficient. So yeah, we have basically established this is also false because Markov localization deals with discretizing the grid. So every time the probability that the robot is in a particular grid or in a particular element will have to be updated for each and every uh, state. So that makes it inherently inefficient. So that is also false. So in that regard, the false statements are option C and D. So the correct answer to this question is option C and D. This is for question 7. And for question 8, What do we have? Question 8 is, yeah, for a robot moving in negative y direction in the global coordinate frame and which uses inputs to predict the position estimates, for such robot, its position estimate will have, okay, for example, I'll simply draw a representation of a differential wheel drive robot, X and Y. So these are the wheels at either end of the chassis. And it also says the robot is moving in negative y direction. As this is the preferred motion of robot in the global coordinate frame and which uses inputs to predict the position estimates. So first, for such robot, the position estimate will have the variance equal in x and y direction, least variance in the direction orthogonal to its motion, least variation in the direction of its motion, and variance will be higher in y direction. So, like if you can recall this error propagation law, or the error propagation law is nothing but the estimation of the variance. Maybe the current estimate of the variance would be maybe ft, then this, what do we have? The variance of the previous estimate, ft transpose, then fq, pq, fq transpose. So based on the previous estimate, previous uncertainty, and these are nothing but the Jacobian of the mobile robot. It's, if you have this px, py, pz as a function of, sorry, the current estimate of position. One second. The current estimate of position is basically a function of x, y, theta. It is also a function of the wheel displacements. And this Jacobian is nothing but dou f by dou x, dou f by dou y, dou f by dou theta. And this Jacobian corresponding to this sensors is dou f by dou SL, dou f by dou SR, the left and the right wheel relative position. And PT is nothing, PT minus 1 is nothing but the estimate, the variance of the previous state. And PQ is nothing but the covariance of the sensors, actually, sensor covariance. If you are beginning from an initial pose, this PT minus 1 would be 0 because you basically know you know exactly where the robot is starting. But as time progresses, if you propagate the variance using this law, you should see that the variance along the direction of the robot is minimal, but the variance orthogonal to the direction of motion would be higher actually. If you can somehow implement this error propagation law, and if you observe this, you can actually see this because for a differential wheeled robot, this covariance would be a symmetric matrix, maybe sigma x, sigma xx, sigma xy, sigma xy, and sigma yy. So if you plot this to be, if you consider this to be an axis of an ellipse, maybe major and minor axis of the ellipse, if as the time progresses, you can actually see that the the size of this ellipse is actually growing, orthogonal to the direction of the motion of the robot. But the diameter or the minor axis would be very minimal, minimal compared to the growth in this major axis. So this is actually a fact, and I don't know if I can show you, if that graph is available, maybe this one, I suppose. I couldn't display this PPT. I only have this images with me. Yeah, this one. So this axis, x-axis, basically in this particular figure, x-axis denotes the direction of motion of the robot. direction of motion along x. And you can see, like initially when the robot is at a starting position, the variance is actually quite minimal. But as the robot moves along x-axis, you can see that how the ellipse of this variance changes. So the apparent change along the direction of motion, the apparent variance along the direction of motion is minimal. But as you can see, the apparent variance orthogonal to the direction of motion is actually quite high. So this is true for any case, or for any case. If it is moving in a curve-like motion, initially there will be minimal variance, but as the robot keeps on moving, the variance orthogonal to the direction of motion would be quite high. So in that regard, what would be the correct answer for our question, which is question 8? Yeah. So we know that the robot is moving along y direction. So variance equal in x and y directions. That is not true. Variance is actually higher in one direction. So option B says least variation in the direction orthogonal to the motion. So that is also false. So least variance is observed along the direction of motion. Option C says least variation in the direction of motion. This is true. And option D says variance will be greater in y direction. That is false because robot is moving along y direction. So variance will be lower along y direction. So the correct answer would be option C in that regard. Okay, so that is this answer. Then moving on to question 9. Okay, so this is regarding the final topic of week 5, that is based on SLAM. It's basically a short form of uh, simultaneous localization and mapping. Localization and mapping. Okay, so yeah, these are more or less statements regarding SLAM, and we were asked to find out the incorrect statements regarding SLAM. So, what is the first statement? It says SLAM is a process by which a mobile robot can build a map of this environment and at the same time uses the map to reduce its location. So, in the earlier case of localization, either using Kalman filter or using Markov, a map has already been fed onto the robot, right? And the estimation is based on odometry and its fusion with the exteroceptive sensors. But in SLAM, the robot will not be given any map. It basically creates its own map online, and simultaneously it will also localize its position, or it will also estimate its position on the map that is simultaneously being constructed. So that is pretty much correct. That is pretty much correct in line with the what is being discussed in SLAM videos. Option B states in SLAM, both the trajectory of the platform and the location of all the landmarks are estimated online without the need of a priori knowledge of the location. So again, that is also not very correct because it should basically know the location, because I cannot make it clear without the slides. So both of this, the location of the landmarks and the platform. Basically, the platform is the mobile robot itself, and the location of the landmarks, maybe the features. Landmarks are nothing but the features that it identifies in its environment. And it basically needs to estimate an initial sense of estimate needs to be given in order for it to estimate the slump. So that is also a false statement. And third statement is basically, oh, it's only an expansion of this abbreviation. It's not correct. It's not simple. It's simultaneous. So that is also false. And D statement, option D states in SLAM, only the trajectory of the platform is estimated online with the need of priori knowledge of the location. Yeah, so only the trajectory of the platform is estimated online. So again, like this is also a true statement. Uh, this has been already been discussed on the SLAM video. I would recommend you to go back to this week 5. It's basically at this end of week 5. It's basically at this end of uh, the last lecture of week 5, and this is more or less at the end of the last lecture of week 5. I know it will basically discuss the concepts of SLAM. Okay. And question 10, we have, I think, 5 more questions. Question 10 basically says, choose the statement that best suits for the prediction of update of a robot. Prediction update of a robot, actually. So again, we have actually seen in localization, there are 2 stages of update based on, the first one is called prediction update. And the other is perception update. And the prediction update is, it happens just after the control signal has been given and just before the current set of sensor reading has been taken. Whereas perception update is right after the sensor reading has been taken, the sensor measurement has been taken. Right. So, for example, the probability that the robot is in current state such that the current, the previous, sorry, the control input has been given and the sensor input is from 1 to t minus 1, just before the current sensor input is taking. And perception update is the update of new position such that the sensor reading from the current state is also available from 1 to t. So which of them is correct regarding prediction update? So option A says it estimates the current position based on previous position and odometric input. So that is true, because at this moment we are not dealing with perception, or we are not dealing with exteroceptive sensors. Option B states it predicts the current position based on previous position and sensor input. That is not true, because prediction is happening just before the current sensor input. Option C says predicts its current position based on previous position and previous uncertainty. Again, that is also not correct, because uh, the prediction basically deals with the location. It's only deals with the mean value, the current mean value of the next stage, and it does not have to do anything with the previous uncertainty. And option D states it estimates the current position based on odometry and sensor input. Again, that is also okay. I think these are more or less similar, I think. So that is also false. Options B and C are saying the same thing. So the only correct answer is indeed option A for question 10. Yeah, if you wish to, yeah, going on to question 11. So yeah, what is this about? This is also about localization. It says Given a differential drive robot which localizes itself in the work environment using the odometry based on the wheel sensor readings, select the correct statement from the following. So it says it localizes itself using odometry based on the wheel sensor readings. It does not say anything about exteroceptive sensors. Odometries are mostly from proprioceptive sensors. And the question basically says nothing about exteroceptive sensors or external sensors that perceives the environment around it. So what does the option says? We have to select the correct statements regarding this scenario. And option A states non-systematic odometric errors can be eliminated by proper calibration of system. So non-systematic errors, or in other words, they are also called random errors, which we know we cannot eliminate it however hard we calibrate it. Only deterministic errors can be eliminated, or only systematic errors can be eliminated. So that is also not true. These are out of control, out of our control. So nothing we could do can help us eliminate non-deterministic errors. So that is a false statement. Option B states the drawback of using just the odometry for localization is that the errors are integrated, leaving no upper bounds for the errors. So for example, if you are getting this acceleration from accelerometer, the sensor is always going to have some sort of noise as well as errors. So from acceleration, if you integrate to find the velocities, and if you further integrate to find the displacement, so as the time progresses, since we are integrating, whatever errors, even though if the errors are small, eventually as the time progresses, it gets accumulated so that after a longer period of time, the errors will become very large. So the uncertainty in the position will become very large for the localization to fail. So this can only be countered using using the features that can be matched from exteroceptive sensors. Using just the readings from purely odometry, the uncertainty keeps on growing until the localization fails. So that is also true, right? Using odometry, the upper bound is there won't be any upper bounds for these errors. Option C states non-deterministic errors are random errors. That is true. They have to be described by error models and will always lead to uncertain position estimates. That is also true. So they can only be modeled, and they are also subjected to a lot of assumptions. So if, for example, in Kalman filter, we actually model the errors. We expect the errors to conform as a Gaussian distribution. So if the inherent nature of the error does not conform to this Gaussian distribution, then there is no point in assuming that the error follows this Gaussian distribution. So only until and unless we are convinced, we cannot have a full estimate of these errors, but we can approximately somehow have some rough estimate of these errors, provided that they conform to some uh, sort of distribution. So that is also true. We can only we can only have these sort of belief states. We can only have some sort of a probability of where the robot is currently. We cannot have an exact estimate. So that also is a consequence of this random errors. There will always be some sort of uncertain. All we can do is we can try and minimize this uncertainty. That's all we can do. And option D states variation in contact points of wheels. Unequal wheel diameters are non-deterministic errors and cannot be eliminated. Is this completely true? Because we have already seen in one of the earlier questions, unequal wheel diameters are deterministic. Because it's fully part of a robotic system that we are designing or we are developing. So if there is an unequal wheel diameter, we can calibrate it or we can make it better so that the deviation between the wheel diameters are more or less non-existent. It's part of a robot that we have full control over, or we can have a full influence on. Whereas in the case of a wheel, the contact point of wheels, we can only tune the wheels, and the contact point of the wheels also deals with the environment. The portion of the environment where the robot is in contact, we cannot have full control over it because environment is external to the robotic system. So we cannot have a full-on effect on this environment as we would have on the wheels of the robot. So only one part of this aspect can be calibrated, whereas whatever is being part of this environment, we cannot calibrate. So that is also a source of. This is basically a source of random errors, right? Contact point of wheels. This is a source of random errors. So because whatever is contributing to the contact point, which is part of the robot, we can have some sort of an influence on it. But that is the extent of the influence that we can have. But the other party, maybe the contact point of the wheels, there is also an element of environment on it, the floor, for example. So we cannot fully influence, or we cannot fully uh, make the floor to be exactly how we intend it to be, because floor is actually part of an environment, and if the robot is actually operating on an unstructured environment, we cannot do anything about it. We cannot do anything about this environment. So that comes under part of random error, whereas wheel diameters are uh, actually deterministic. So this statement is not fully true, it's partially true. So in that regard, we can dismiss this entire statement to be false. So the correct statements are options B and C. Only B and C are the correct options. Okay, so this is question 11. Moving on to question 12, which is here. Again, this is also deals with the prediction and perceptions, what we have seen in previous questions. The belief state calculated before the new observation, just after the control input is defined as, is it the prediction update or the perception update? So again, what we have seen, this is the prediction update. This happens just after the control input and just before the new observation, just before the new sensor observation. This is from the sensors, and this is UT, the control input, to the wheels. That is nothing but prediction. And perception comes after the new observation using the sensors. That is where the perception comes. Prediction is before the new sensor observation. So, yeah, that is also true. Prediction is actually the right choice. And going to question 13. Again, this is also, we have to choose the wrong statements. This is also regarding localization. So the first statement says, due to discrete representation of space as grids, Markov localization is computationally expensive than Kalmar filter localization. So that is also true. That is actually a true statement, because Markov localization essentially deals with discretization of the space around it. And question B says Markov localization is capable of recovering from ambiguous situation. That is also true. If you kidnap a robot from its current location to another location, the Markov localization can recover after probably a few iterations. Whereas that is not the case of a Kalman filter localization. And option C says the advantage of Kalman localization over Markov localization is that Kalman filter is more robust than Markov localization. So that is actually false because actually Markov is more robust because just like I have said, if you kidnap a robot from the current position and if you deploy it on some other location, Markov localization will work, but Kalman localization will fail because of that. And because of that, the Kalman will only work if the robot is starting from an initial position. The Kalman localization should know exactly its initial position, where it is exactly is. Then only it will work. But if it is simply kidnapped from its current position and if it is simply deployed on another location, the uncertainty will actually grow so that the Kalman localization will essentially fail. And in that regard, you cannot call Kalman to be robust because if the uncertainty actually grows, or if it is in collision with some obstacle, and if its sense of location is lost, it cannot fully recover once the uncertainty has grown beyond the threshold. So in that regard, Markov is more robust, and Kalman is not as robust as Markov localization. So that statement is actually false. Uh, then what about option D? Kalman filter localization models measure noise as Gaussian distribution. That is also true because that is also one of this assumption in developing this uh, Kalman filter based localization. We model this error, sensor errors, and sensor noise as Gaussian distribution. And the next estimate, the current estimate of position and the current estimate of this covariance metrics are all based on are all dependent on how the errors are being modeled. Okay, 1 second. Okay, so yeah, in that regard, option, I don't know what. So this was true. Option B was also true. We have established this was to be false. And what about option D? Kalman filter localization, that is also true. We just established that. The final option, option E is Kalman filter localization is inherently more efficient than Markov localization. That is true. Because Kalman filter localization does not deal with discretizing the space of the workspace of the robot. So the only wrong statement it appears is option B. This is actually the wrong statement. Okay, so we'll discuss two more questions and we'll wind up today's session. Question 14 is, question 14 is arrange the following steps in the correct order of map-based localization. So, yeah, what do we have? We have matching observations and map, observations with onboard sensors, estimation, prediction, and measurement. So we have been given 5 steps for localization, map-based localization. What is the correct order for map-based localization? So we always begin our localization based on previous estimate and odometry. So if you have the previous state, maybe if this is xt minus 1, so this is the previous state, and if you know the input that you are supplying onto the wheels from the the previous position, and if you are giving this input, where would it be? It's present position. This is current position. So this is purely relying on odometry. There is no sensors. We haven't introduced any sensors as of now. It's pure odometry. So the first stage would be prediction. That is option 4. Then what is the next procedure? So once we have predicted or once we have estimated the current stage, then we would observe, the robot will observe the surroundings using the sensors. So the second would be observation using sensors. Maybe I'll call this as exteroceptive sensors. So for example, this if I call this as ZT, observation using the sensors and using prediction, and if it has a map, it can locate itself on the map. For example, if the robot thinks it is at XT, this XT is actually referred with respect to a map that has been loaded onto the map. That has been loaded onto the map. Then what do we do? Then it basically, what are the remaining steps? Then we have eliminated options 4 and options 2. Next, we have matching observations and map. Then we have estimation, position update. Then we have option 5, that is measurement prediction based on prediction and map. So yeah, the next procedure would be the prediction, actually, prediction on map. Yeah, so once it has the sensor reading, it basically predicts its next position. So if I go to 5, where should it be? Measurement prediction, actually, measurement prediction based on map. Because, like, for example, if this is a map of a robot, I'll call this as map. This was the prior location, xt -1. And if you give some control input along this direction, ut, and if the robot is at here, xt, it'll basically locate itself based on a map that has been already given onto this robot. So within this map, when the robot is at this position, it only thinks that the robot is at this position. This should be seeing some obstacles. Actually, this is one obstacle. This is another obstacle. This is another obstacle. So it should be aware of. It should basically correlate with all the nearby obstacles. This obstacle is maybe around 5 units from this location. This is maybe from 5 units from its location. This is also from 5 units from its location, for example. So based on the map, the robot at XT should be seeing all these obstacles. Then what is the next step? So this is purely from the measurements. Then the next step would be matching what it is being observed, matching with onboard sensors. Right. So according to the map, the robot thinks there are obstacles, equally distributed obstacles, maybe around 5 units from its current position. But from the sensors, it may be seeing something different. Right? According to the map, it should be seeing one thing, but the sensors are actually seeing something different. So it should be mapped. It should be matched. What it is supposed to see from the map and what it is actually seeing, these differences should be matched so that it can basically give a corrected estimate using corrected estimate after this matching. So if it is actually matching in pretty good, it does not need to do anything further. It does not need to revise its estimate. If the matching says there is a difference between observations and map, then it has to revise its estimate. So the final process is basically estimation. estimation, position update. Position update based on its map and the observations. So in that regard, the correct option is 42513, option B. I'll also show the slide, maybe a flow chart that will depict the same. See, initially the robot will be here. It predicts its current position from it predicts its current position from odometry. Odometry is actually from this encoder it can actually these are proprioceptive. So encoders will give you idea about how much the wheels have moved and the current position of the wheels and how much control input basically that you are moved. And using the map database, the next position is updated to the map database, and this is actually compared with what the robot is currently observing. So what the features that the robot should be seeing from the map and the features from the environment that it is actually seeing is being compared. And if the observations are compared, the new position is actually updated. If it is compared, the previous position can be taken to be a good estimate of the position. If it is not matched, then the corrective measures or the corrective control input can be further taken. So this thing goes on a loop, on and on, as long as the mobile robot is actually in operation. Okay, so moving on to the final question for today's session. Yes. Okay, so something is a process by which a mobile robot can build a map of this environment at the same time use the map to deduce its location. So this deals with building of a map and also to deduce its location. So none of this actually matches perception, localization, mapping, prediction. Does not really cover building of a map. The only thing that covers building of a map is SLAM, simultaneous localization and map, which is what we have covered in the last lecture of week 5. Okay, so yeah, with this, I have to wind up today's session because usually we could take it up to 2 hours. We would discuss a summary of all the topics that we have covered in the in that corresponding week, so that we could get more insights while solving this question. But unfortunately, I think I cannot still access my presentations. So this seems to be a critical issue. It seems like a big issue because normally these things will never happen. That entire website uh, it has been blocked, I think. So I'm not sure whether this is a hacking attempt. It earlier it felt like it has been hacked. I don't know whether it is my personal account or whether it has it has been blocked throughout. It has been affected everyone using Overleaf. Earlier, I thought I saw a message actually. So I think I suspect hacking also. So yeah, leaving that aside, I'm sorry that I had to, limit myself for this week's lecture. Yeah, maybe by next week we can discuss the remaining topics on, path planning. So that is more or less an extension of what we have covered from week 4 and week 5. Next week will be path planning. So yeah, maybe with that I'll see you for next week. And I am really sorry for how this lecture has turned out to be. Right. So if you have any questions, let me know. There is also one more problem. I couldn't access my discussion forum. So there is also some other issue because The credentials, it seems that the credentials now require two-factor authentication. Two-factor authentication. So yeah, I think unless the other end, I think from NPTEL authenticates, I don't think I can log in from my end. I have to check that. Maybe by next week I'll rectify that issue. So if someone is actually posting some questions on discussion forums, please give me a few more days so that I can reply that back to you. Okay, so until next week, goodbye. I don't have anything further to add. So yeah, I'm winding up the session. Thank you.